Hey, how's it going? We're going to take a look at a second complex circuit since we had such a good time with the first one. The second one linked to the agenda is here. We'll start out just by taking a look at how it's different than the first one and mentioning a couple of things about the first one. So in the first one, from the first Ed puzzle, we had a 24-volt battery pack, and then we had a bunch of resistors, and they had different connections. So flowing right through this first one, we'd say it's in series, but then the wire splits, so we have two parallel branches. And then it comes back together and went through another resistor down here. So it's sort of like three things in series. We had to remember those rules. And then it's sort of the second thing here is just two branches that are in parallel. So you need to remember some parallel information or rules. The second one, not that much different. It's just a little bit more complicated. And all that is different, really, again, it's sort of three things that are in series with each other. It's just the second element here really is two parallel branches. And now within those parallel branches, we have series connections. All right. So let's analyze this again. I have labeled them on my chart behind me here, but it is 1, 2, 3, 4, 5, 6 to keep track of things. And the chart I'm talking about is this chart over here, again, linked to the agenda. So we're going to take a look at this second one here. So step one is trying to resolve it or simplify it down equivalence-wise, and then figure out total resistance. And then when you have total resistance, you could figure out with a V equals IR using the battery, figure out how much current leaves the battery, and then we'll go from there. So let's figure this out. So it's similar to last time, except we can't treat all of these things in parallel because they're not all in parallel with each other. It's really just there's two parallel branches. So what we'll have to do is we'll have to find the equivalence of each branch, and they're using series rules, and then consider the equivalences in parallel. I know, awesome. So a 6 and a 4 in series, this branch here has the equivalence of 10 ohms. This branch of 3 and a 4 in series with each other has the equivalence of 7 ohms. So now we're going to try to simplify that down and see what is a 10 and a 7 in parallel. What are they equivalent to? So 1 over, following parallel rules, 1 over what we're looking for, resistance total or equivalence, 1 over 10 plus 1 over 7. So you can find common denominators, no big deal, but let me just show you real quick again how to do that on your calculator. I would do 10x to the negative 1. I hit enter. And then plus 7x to the negative 1, I hit enter, and I get a number. But that is not my answer. I need to take the reciprocal of that. So if I just leave my answer in my calculator and hit x to the negative 1, it'll flip it over, and I get the total resistance of that section. So resistance total for this parallel section should be, let's see, 4.12 ohms. So now I can kind of do what we did last time, where I know a 3 is in line with something that's equivalent to a 4.12, and that's in line with a 9, so we can add them up with our series rules. So let's figure out total resistance or resistance equivalent for the whole circuit, and we're going to use our series rules. So it's just going to be 3 plus what this section is equal to, 4.12, plus the 9. What is that? That's 16.12 ohms. So we got total resistance for the whole loop. So we can put that in our chart here. So equivalent resistance for the entire thing, 16.12 ohms. Okay. Now we want to figure out current leaving the battery, and then we can determine, we'll know that all of it goes through the 3. We can figure out how it's splitting, and then we know all of it goes through the 9. We can start finding our voltage drops. This is great. So let's figure out that total current. So we just need to do an Ohm's law for the whole thing. So let me just, you can, always go back or whatever. So total resistance, 16.12. Let's do a V equals IR, or Ohm's law, for the whole circuit now. So battery pack 14 equals what current? Resistance 16.12 divided over, looks like less than 1, so it looks like current is 0. I think I wrote it down somewhere, 87 amps. So now we know the current leaving the battery, and we know that that amount is going to go through the things that are in series and get split up as it goes through parallel sections. So we can then start figuring out what are the voltage drops for the different areas. So I'm going to focus on kind of the easier areas. And again, so with sort of three things in series, there's going to be three ways that this 14 breaks apart. It's easiest to find it here. You can use the total resistance of this whole section and find the current that's sort of going here, but that's a little bit more complicated. So I'd probably go here and figure out from what's left of the 14, what's the drop for this whole section. Then we can figure out the current moving through each branch. It's going to be awesome. All right, so the first one, going through the first one, resistor 1 on our chart there. Let's figure out the voltage drop at resistor 1. So all you need to do is, we know the current going through the resistor, so find the delta V. Delta V, so delta V equals IR. We know that the total current, because it's in series, the total current of 0.87 is getting to a 3 ohm resistor, and I think I calculated that as 2.61 volts. So of the 14, 2.61 is already being used at that first element. Let's find out what it is down here, and then we'll know what's left for that nasty section. So let's do it. V equals IR over here. Excuse me. So we know again, because this is alone by itself here, that all of the current that left the battery has to flow back through here. So we know that all of the current, again, current was 0.87, so 0.87 times the 9, and I wrote that down. What is that? 7.83 volts. So with this drop and this drop happening at these two resistors, we can kind of by subtraction figure out what's left of the battery. So let's do that. So the battery had 14. So let's subtract 7.83 and subtract 2.61. So it looks like what is left for this entire section to drop is 3.56. So for this whole section, delta V is going to be 3.56 volts. So let's see what we can fill in the chart. We got to be careful with that nasty section, and I'll explain. So voltage drop through the first one, 2.61. So 2.61 volts, and we know the drop happening at the 9 also, 7.83. 7.83. Now we need to be careful, because we can't just say that everything else is dropping by that 3.56. It's that this both branches, because things in parallel get the same drop. I know it's confusing, especially at first, or if you're not interested in this stuff, I know. But this is the drop for this whole parallel section. There'll be mini drops at the things in series that'll add up to the branches available drop, and that'll happen here and here, here and here. So the drop here and here should add up to the branches available voltage, and the little drop here and here will add up to the branches available voltage. I know, it's awesome. So let's figure out what current goes through those two branches there. So I'm gonna leave this alone for a second. Oh, we know current here. I should have put that in already. So that was the 0.87, 0.87, and also 0.87. Again, because those are really just alone by themselves. So we know full current going through those resistors, easy to find the drops. And again, we'll do that power column last. Let's figure out what current goes down this branch, and therefore that current will move through the 6 and the 4, and then figure out which current goes down this branch, and that current will go through the 3 and the 4 of this branch. The current that's going to go down these branches is going to add up to what is possible. Now, what is possible is what I mean by that is what gets there. So what gets there current-wise is 0.87, because it flows from the battery, flows through here, and then things in parallel split the flow, split the current. So we'll figure out how much current of this goes down each branch. A little bit more, I suspect, down this branch, because it adds up to a total of 7 ohms of resistance, and a little less going down this branch, because this branch is a little bit more difficult with an equivalence of 10. Again, a 6 and a 4 in series is equivalent to 10, and a 3 and a 4 in series is equivalent to a 7. I know, this is great. So let's figure out how much of that current gets split when it gets to these locations. So we can do that in a couple of ways. So let's figure out how much of that current splits. So let's say we know the drop for this whole branch and the drop for this whole branch. Let's do some quick Ohm's law. So V equals IR. So 3.56 equals what current down a pathway that has a difficulty of 10? And with the same drop, parallel branches experience the same drop. What current goes down a branch that has a difficulty of 7? So if we just solve those out, we can figure out what goes down each branch. And let me do that, and we'll double check. So 3.56 divided by 10, and 3.56 divided by 7. So it looks like, of the available 0.87, it looks like what goes down this branch, some people label this stuff as I1 and I2, but I think we're going to get really confusing here. So what goes down the branch that's 10? So I did the math with the 10, and it looks like, can we still see this? I equals 0.36. Is it in there? Yep. And what current goes down this branch? 0.51. So what is that? 87? Boom, adds up to the 0.87. So now we know the current moving down these branches. Since these elements are in series with each other down the 10 branch, I know that they're both going to get the same current through them. Isn't this great? So 0.36 goes through 2 and 3. So current through 2 and 3 is the 0.36, 0.36, and 0.36. We also just figured out what current is going to go through what we're calling resistors number 4 and 5. That's the far branch. That has the equivalent resistance of 7. So 0.51 will flow through this one and that one because they're in series. So 0.51 will go through what we're calling 4 and 5. So 4 and 5 get 0.51 and 0.51. Okay, back to figuring out now voltage drops. So what we were saying before is this whole section experiences a drop of 3.56. Let me make some room here. Can always go back in the video if I'm erasing some of the math here. Okay, so little drop here, because we're almost done. 11:30. Okay, we're almost done. So what little drop happens here and here, again, will add up to the drop for the branch. And there'll be a drop here and here that will add up to the drop available for the branch. So let's figure that out. So now we know the current going through each thing. So we just have to do a little V equals IR. I guess we're going to have to do it 4 times. So let's do it for resistor, what we're calling resistor 2, the 6 ohm resistor. So if it had a current of, so what is the little drop? If 0.36 goes through a resistor of 6, and then the little drop that happens when a current of 0.36 goes through a 4. So 2 little mini drops, and gosh, I hope they add up to 3.56. Let's check the math. 0.36 times 6 is that, and 0.36 times 4 is that. Woo, and I think it adds up. So let's get those numbers up there. For this one, it is, so delta V would be 2.16, and this one would be 1.44, 3.7, 3.5, 3.6. Close. 3.56, 3.6. A little bit of a rounding thing. So let's get those in there. So the 2 drops. So the drop, so we're talking about for resistor 2, the drop is resistor 2, the drop is 2.16. And at resistor number 3, the drop is 1.44. Again, just some slight rounding. It keeps us from adding up perfectly to 3.56. And then the final branch, then we can calculate power, do a final power check, because that's how you know everything on the chart kind of works out, because you find your power column by doing math across. And then if it does add up to the whole power for the circuit, then you can kind of be comfortable that this is all correct. So I'm looking forward to that moment. So down this branch, so little drops again. Little drops are happening. So little drop here and here. So let's do the math similar like we just did down this branch. So the delta V happening. Current down the 7 branch was 0.51. So 0.51 going first through a 3 ohm resistor and then through a 4 ohm resistor. And again, those should add up to basically 3.56, we hope, with some rounding. So let's check that. 0.51 times 3, and 0.51 times 4. So I get, for the 3, I got 1.53, and for this one, I get 2.04, 3.57, about 3.56. I can live with that. Rounding. So through the 3, the drop was 1.53, 1.53, and through the 4, 2.04, 2.04. Whew. All right, let's let's check that power column, and hopefully everything will check out. So be patient with me here. Let me do the math. So we got 2.61 times 0.87. So I got 2.27. I get for this one 2.16 times 0.36. I get 0.78. For this one, I get 1.44 times the 0.36, and I get 0.52. Rounding as we go here. Rounding. 1.53 times 0.51. Of course, what am I doing? I'm doing the power formula. It's current times voltage. So I'm just multiplying the first 2 columns to figure out my power column. That last one was 0.78. And power consumed at element 5, that's going to be 2.04 times 0.51, and that is 1.04. And finally, last element, 7.83 times 0.87 is that, and I get 6.81. Let me, oops, so I didn't really mean to do that, but let me tally that whole column now, and we'll do a power check for the entire circuit. So I've got 2.27 plus 0.78 plus 0.52, tallying the last column, 0.78 plus 1.04 plus 6.81. What do I get for whole power? I get 12.2 watts. Let's do a check for the entire thing. So we want to do an I times V for the whole thing. I think it's going to work out. So power, we're doing a power check. So this was the power when we added up that power column on the chart. And we'll do an IV for the whole circuit. And it looks like it's going to check out here. So power is IV. So if we take the total current, 0.87, and multiply by the voltage of the battery times 14, what do we get? So 0.87 times 14, and I get 12.18, 12.18 or 12.2. Yes. Pretty awesome, isn't it? I'll see you on the next one.